So hello everybody, please let me know if the sound and the video is okay, and like we'll start just in a second. So is sound and video okay? Sound and video okay. And then we'll start in a second. And also, meanwhile, please get the template 9.2 from the Google Classroom. I see only three people online. That's not so cool, but the less people are attending, the harder it will be for their homework, probably, because otherwise you cannot ask the questions. Or if you just send the questions in text form, like not engaging format, it might not be answered as quickly as in the chat. Okay, so great. Seeing Armands and Kristaps. Interesting that YouTube shows really low count of live viewers, but let's see what's actually happening. So the template can be you can get template also from the link that I shared in the chat here from Mega. So we will implement really intensive stuff today. I didn't have time properly to re-evaluate and grade all of the new homeworks that were submitted, but I'll do that hopefully for tomorrow, or worst case next week. So the homeworks still count as the way to pass this course. And so today we'll work on really exciting and fun stuff. Seems like really low count of viewers, but I'm not sure, like, did everybody else give up on the course? Let me check the courseworks. I know that some that are not right now connected were quite okay, like doing quite okay so far. It seems like that there was really low response on the homeworks from last two sessions. The last two sessions were the proper sessions where we started migrating to PyTorch, and the PyTorch is the environment that we're going to use from now on only, and it will be like really powerful way to do the either some production models or research models. Like that's one of the best ways. So here we have some small image of what convolutional neural networks are. From classifying the image of Tesla and then giving out from the fully connected layer the probability distribution with the highest probability for car. So the probability distributions of the iris data set that we just looked at in what is your homework, you already know how to do. So then there's the convolutions. So these are the new layers, new functions. And then there are pooling layers that are also new functions. We will look at both of them. So, and the idea is that you have high resolution image and you somehow compress that knowledge down to some very low dimensional vector that you can pass to the fully convolutional, fully connected layer or linear projection, basically, to project that vector on probability distribution with the predefined ground truth classes. If you have some questions about the stuff at any point, you can try to write in the chat, and we'll look more. So please also get template 9.2, the template 9.2 or the template from link. That's going to be needed today. So the another way how to look at these models, you will code the kernel function today yourself, and you will understand this image perfectly after today. So the idea is that you have some image as an input. So this is actually a color image, so that means that there is RGB channels. But today we're going to work with grayscale images, but it can work with any images. Then you have the feature maps. So the feature maps you get by applying the kernel function. So this small rectangle is the kernel. The kernel is just a small matrix that you multiply and sum together, and you go over this image like in specific pattern and generate the feature map. So like if you sum all of the, like multiply and sum all of the pixels, and then you insert this one singular value in this new matrix that you call feature map. And then you do this again for the next one, for the next one, for the next one. And the interesting thing is that you increase the channel count, so you increase the number of feature maps. So actually in this image, if this would be a grayscale, then this would be correct image. If this is a RGB, that means there's actually 3 feature maps already present in very beginning. And yeah, so you exchange the resolution, width and height with the depth, and depth is the number of feature maps here. And then you go down, down, down until you have just a one-dimensional large sausage that you can pass to the linear projection. So that's a really high, like looking from the very high logic, but it's not everything. We'll go in much deeper details. So another way to look at this is I think it was from Udacity course or somewhere, but the best resource that we will look today is from Stanford. The course that I also mentioned in the preparation materials. So here again we have the situation where what I said is that the feature maps, the depth is RGB pixel values, the colors. So each of these like kind of layers of this box contains so the 3 layers. So one is red color pixel intensities, green, and then blue. And then you pass this function. This function is going over all of the positions of this input image with a cat, and generating out a smaller version of the same image, but with the higher dimensions of the depth. So then this is not anymore RGB, but then there is like higher dimensions. And so we need to look at this even more with some other ways, and then I'll try to explain also some other ways. So originally, I think that so if you look historically, convolutions was one of the ways to improve the performance, because if you just put if you have this image and then you just try to unfold it in one dimension, just view in one dimension and then pass to the fully connected layer, that is really expensive like dot product operation that would be like very slow and also resource intensive and also kind of not really controllable that well. And and then they tried to optimize it using the convolutions, and then it turned out that this approach of using convolutions and these feature maps that you actually see also in this image, the feature maps, especially in the first layers, the actual learned kernels, looks very similar to Gabber patches, and the Gabber patches are then something that the feature engineering was done manually some long time ago, and also where you see in biological AI retina, biological neural networks. So in general, this architecture is quite similar to biological architecture. In the just in the responses of the first layers, so yeah. Here you see again, so these are the learned filters, probably for the first convolution layer, So in the very beginning, these are random, and then they learn that they should pay attention to very specific things, like for example, where the color changes in some very specific pattern, where there is kind of like edge or corner or something, and they learn this by, like the model learns it by themselves using the partial derivatives and backprop, and the output of these learned kernels matches, as I said, the way how Gabor patches work. That's from the ophthalmology, where you make where you study the human eye, and also like from other biological, neurological perspective with the retina neural networks. When they try to capture those responses, they look similar. So that's one nice feature, and the way how this actually works, I think, really nicely shown here. I will share the link also in the chat here. This we can stop also the process, but the idea is that you have three-dimensional color image here on the right side. So this is a color image, right? And this is not just color image, but it's also a padded color image. So the color image is itself in the blue area, and then they have zero padding around it. So that's one thing. Then we have some filters, or those kernels that we want to learn, and they are also quite interesting because so the output here are 2 channels. So the input was 3 channels, but output is 2 channels. So normally actually you would go another way around. So the input is 3 channels and output is 4, 5, 6, 8 channels or more. But in this case, they at least then it would be take too many calculations. So they showed the process in other direction. So that's fine as well. So you see that what they do is that they calculate a pairwise multiplication by each of the cells between the filter that we learned that is random in beginning. So each cell is multiplied together, and then they sum all of those cells together, and then they place that sum value here in the corresponding cell for each of the filters. So if so there are 2 filters. The first filter W0 is responsible for the 0-dimension output feature map, and this one is responsible for the 1st-dimension output feature map. And in order to do this, they actually they sum so they multiply all of these, multiply all of these, multiply all of these with corresponding matrices. Then they sum everything together. They sum all of the red blocks together, and then they insert in this one small green block. And what the effect is that we changed the channel count, and we also changed the dimension. So the dimension here was much bigger than this green output. So I think there was also some formal way to describe this function. Let me see if they have somewhere. So this is called kernel function because you repeat it for the vectors many times. But I don't see actually here the formal definition, but I have at least some that I can share with you. So this algorithm is much better understood by looking at it and coding it. But so if we just formalize this kernel function, we can formalize it by dot product, but it will not be that visible to see what's actually happening there. So by the way, if you have some questions, ask in the chat. Meanwhile, prepare 9.2 template. We're going to work on this shortly. So let me see. And I also shared the template in the chat. So let me see. I have some equation for this operation, but let's see. Can I latex it? Seems like that I took that equation from one source. I don't want to write it myself because it is not really properly. So again, I will not probably write the equation for this particular kernel function because first of all, you need then multiple sum signs there, and also like the way how you select this region out of this is really not mathematically nicely written, but you can write it, of course. So that's one of the things. But we will code it, and then you will understand it better definitely as well. So there is another thing that so if we have this kind of function where we can choose how, like, what is the padding, we can add, let's say, 2 lines of padding around it. We can change the filter size. So now it's a 3 by 3 by 3, but this could be also, let's say, 5 by 5 by 3 or whatever. So the only thing that we need to keep is that input dimensions 3 must be the same. Okay, nice that we have some questions. Is the output image smaller than the input image after using kernel on it? Right, so the usage of the kernel is when you, so this is algorithmic way. You can parallelize this function. That's why we're going to work today with actual GPUs. Today we will start working with the Google Colab and GPUs, because when you parallelize these functions, they work so much faster. But the idea is that as you look in this animation, that this result of reducing the size of the input from this blue one to the green one is the result of using the mostly the result of using the stride. So the stride means that you see that it is jumping over one element always. Like if you want, you can create stride 1, and then it would not jump over the element. It would just go one element step by step, and then the output will be the same as the input. And that's also completely fine in some situations. So it just is this algorithm itself defines the way what will be the size of the output. Hopefully that answers the question, and if you look at it, maybe it also helps. Oh, nice, I found another picture that I want to share. I will share another picture, and then I will also share the formula. So there is a mathematical formula, that one is really simple one, that you can use all of the parameters that you have here visible in this algorithm to calculate what will be the output size of those green boxes. So the green feature maps, and that's very useful when you want to like construct your models, because you need to keep track of the sizes. If you don't know the sizes, so you guess some kind of kernel, you guess some kind of stride, some padding, and then you run it, and then you don't know what is coming out. It's not a good situation. So let's keep moving. So the slide number 3 then. Here's another nice representation of what is happening there. So I like this a lot as well. Some person made it really nicely, clearly defined. So the idea is that you have this kernel matrix. So the kernel function itself means that we can use the same function for the set of data that in this case is the input image. Like in parallel, they are not interdependent, and and basically usually kernel functions are associated with vectors. So here there is the idea that we multiply element-wise each of those values, and then we sum all of them together, and then we get some value that we put in the middle of that other like output of that that pixel that is coming out. So the other fun thing is that of course we can fill the like the lines around this new matrix, the new output feature map. But the only way how to do this is then if we pad. So if we have the padding of the source map, then of course the output of that kernel around the edges would be also nicely filled. So that's one thing. That's cool. So, and then the last bit that is missing before starting to code this algorithm is that we want the some way to calculate the new output feature map, and this is how it's calculated. So there is some parameters. So one is the input features, so that we know, like RGB three channels, right? Output features we invent ourselves, doesn't matter, like it usually should increase. Then the kernel size, again, we choose ourselves. This is just that matrix size, like often used as a 3 by 3. Then the padding, again, depends on what we want to do. Like if we want to keep the size, or maybe some objects are very close to the edges. Okay, we'll talk about also the objects just in a second, but maybe we should do this a little bit later. I think we should do this a little bit later after we start coding the stuff, because then you will understand it better. So then the stride is this jump, you know, like the how long are the jump when you move over all of this matrix, right? So these are the components, and this is the formula for calculating this output. So that's great. Okay, before starting to work on our project, we will use today a new data set, and in template it's already coded for you. First time you run it, it will take a little bit longer time to download all of the images. So this data set is called fashion MNIST. So this is a grayscale images of fashion items, and they are classified in 10 classes. 10 classes, thousands of items, I think like about like 80,000 or something. So, and the size is, so the shape is one, so the grayscale 28 by 28. So that's the image, very small images, X shape. And the reason why it's 28 by 28 is because the MNIST, the character recognition dataset, very popular, very old, is the same kind of dimension. So we're gonna make a model that can predict which from the image, which is this item of the classes. Is it like a bag, shoe, trousers, whatever? And we will make the, as I have in the task 9.2, you cannot use Torch NN Conv2d, so you cannot use ready-made function. You need to make your own convolutional function, because in this course, actually, I know that when I talked with Linda, she said that you will have, or you already had, some in-depth convolution course. So now I just want to cover the functional basics of this. I don't want to go in all sorts of convolutional models. There are like a huge set of convolutional models that you can explore, and they are in very different properties. And like there are some are like extremely complicated to code, like instance segmentation models with like. Probably Linda would show you how to code all of those crazy amount of functions inside one small model, like not small but one large model. So that's one direction. But we will look very like loosely on these things. At the same time, I will not lose the track of the functions. So I mean, we cannot just like use ready-made stuff and don't understand how it works. So we will do this ourselves. So, but that, again, we cannot do everything ourselves, unfortunately, because we have limited time, and that's why some functions we will use ready-made, but the main functions we will not use already made. So let's go to the code. So the template should be ready for you already. So I will go over some of the details of this one. Meanwhile, let me give me your feedback. Is the template ready to work? Is the template ready for work? Plus, minus, and if minus, then what's the deal? And then I will go over quickly some of the details of this new template. there are some changes from the previous templates that I gave you. Some significant changes, some not so big changes. I will explain. So I see only 2 pluses. At least we have 2 active students today. Too bad for others. Hopefully they can see this video later and don't so that they will not have the option as Armands did to ask questions. So that will be sad. So anyways, here we have the wrapper for the dataset. Before we didn't use the wrapper for the dataset. So again, here this is very interesting thing that you see it is overriding the operators of Python. So the length function. So you can ask length of the list, right? If you ask length of the list, then it will just give you length of the list. But you can override that operator. If you ask some like any object, any instance of object length, if you have implemented this function, it will return what this function returns. Also with the get item. So with get item, it means that like any operation, like if you have something, let's say there is with the list the same stuff, but here if this is a data set, you don't need to write this as just an example. So data set, and if I ask some index 0 or if I ask ds index 2 or something, it would get in this function. And the way how we use it, it looks like this is a list or something, but this is not a list. And the same way goes with the PyTorch and NumPy operations of mathematical operations, where you have pluses, where you have the symbol interesting of the dot product, right? Matrix multiplication, or if you do minus, plus, any arithmetical operation, they are not doing arithmetical operations on those arrays or the torch tensors. Their torch tensors have implemented these operators, and that's why it works. So that's just small note. Then also we have data loaders. So that's again, before we selected batches ourselves from array. Now, if we have a data loader, we can select the batch not by using the syntax of selecting from NumPy dataset, but do this automatically using data loader. Plus, there is additional benefit of shuffle. So it means that we want to shuffle the training dataset, but we don't want to shuffle the test dataset because we want to examine the same examples between the epochs. So that's one thing. Then there is a small template that we're going to code for convolutional 2D function. So the main things are here, except the main thing. So then the model itself, I will help you to set it up. And then for the homework, you will have your own model to code. Then there is so there is some places with to do that we will add for GPU support. For GPU support, I think we will do the GPU support probably like one of the first things, because that will help us. That will be needed also in that conv part probably. So then we have some interesting dictionary where I store metrics. Now, right now I store train, loss, test, loss, train, accuracy, test, accuracy, 4 metrics here. But you can add more metrics. And in the homework, I'm not sure, did I ask you to do the F1 score or something? We will probably have some additional metrics that you can calculate. Then there is the same thing as before, epoch, data loader loop, and then the batch loop. The batch loop here have the X and Y already prepared nicely for you. So the X is the batch of the images, and Y is the one hot encoded vectors. So then we need to do the loss function. Then I also provided you the calculation of the accuracy and the plots at the end. So that's about it. So let's ask the question: is the code clear plus minus, and if something is not clear, let me know what is not clear so far, because of course the to-do parts are missing yet. But if you're looking at the code something that is not clear, let me know right now. If everything is clear, type in plus, please. Please go over the code, and I see like kind of two pluses. If you don't know something or not sure about something, you can share the line number or then I can explain it. Okay, I see kind of two pluses, but I think there is at least 3 active students right now. Anyways, hopefully all of you could be active during this session. So I think let's start with the model. So starting with the model, maybe we should define first that because to create the encoder or this convolutional backbone, it means that we still need to use that formula that I shared you in the Jamboard, because at the end we have fully connected layer and linear layer or fully connected or linear projection. Okay, nice. Somebody is asking questions. Line 16. Class name. Not sure about what's wrong there. Maybe I guess there is a mistake in the typo, I guess. Maybe there is a typo in language, like in English language. Yeah, fashion. Sorry. Yeah, nice. Thank you for that. But I don't want to like break the code. But yeah, so there is a fashion. Right now it works better. But then if you change this name, then you need to also change it here. Yeah, I didn't see that one right. So thank you for that. We'll check it for fashion. Right. Thank you for that. Anyways, okay, let's start with the model. But in order to make a model, the convolutional backbone, we need to have another function. I suggest that we make it as a function, because otherwise we need to always write the same equation, and that's not something you would do in like programmatic way. So here let's call it get out channels. I don't get the class name. What is meant by mnist? Right, the mnist is the I will check what is actually the. I think it was something like Montreal. Something with Montreal, because I think it was from that area. But the idea is that was very historical, very popular data set from LeCun, who is one of the modified. Sorry, it's not Montreal. Modified National Institute Standards of Technology database. So. If you type in mnist in Wikipedia, you will find it. But this is really old data set of the character recognition, and basically they kind of updated the theme for this one with the fashion. So, do you mean what is passed to the class? So the class. So if you think about, if you're asking about this part we covered a lot before. So this is object-oriented programming. This is inheritance, right? We are inheriting the this torch dataset, but probably you meant something else. So it is basically class meant specifically for dataset, right? Yes. So this is a wrapper for dataset. I like that, those questions. I kind of starting to get what you mean by that. Is that, for example, imagine if you have a dataset that is, let's say, 10 terabytes or something like that. So 10 terabyte dataset, you cannot load in the RAM. Right now we are loading in the RAM, this read-only, like our RAM memory. Self data, fashion mnist, loading in RAM. That's fine. If you have 10 terabyte like this dataset, then what you do here is like select some area or where it will be located on your disk, right, on hard disk, and then when you ask length, you would calculate what is the length, and then when you ask get item, you would access probably the hard disk, or you would access like some, maybe it would work even, I don't know, like if there is some kind of distributed computing or something. So that's why you have this wrapper class. This, like, normally when you have proper datasets, you cannot just load them in one array and access it. Okay, hopefully that answers the question. So I started making the function here. So get out channels, that is the function that I shared you in the Jamboard channels. And so I mean not out channels, but out size, sorry, out size. Funny. Somebody had the interesting experience with trying to like load in his computer like really large dataset. Anyway, yeah, so the datasets are really large nowadays. So let's return this function. This function you can implement yourself easily. I could ask to do this live, but if I ask to do this live, we don't have time to do all of the other tasks, unfortunately. So there will be in size, then we need actually also the other parameters, so padding, kernel size, and stride. We need those parameters. So then this is 2 by padding. So this formula just is the like kind of representation of that algorithm that we will implement in just a second. And the algorithm that we will implement can be parallelized, and it's actually parallelized really well on CUDA and GPUs. That's why we will need a CUDA. So get out size. Okay, hopefully if I don't have a mistake in that function, you could write it. So I will drop it in also the Jamboard. So it's on the slide number 4. Then we'll go to the model, and we will need to use that function because we need to construct the model itself. But okay, let's wait for you to catch up with this one. So I don't want to like jump too fast. So is the function okay? So I see we are okay, the 3 active people that we have. Okay, that's great. Happy for that. So let's move then to the model. So we will, in order to construct this convolutional network, and at the end understand what will be the size of the last layer, we need that function that we just implemented. So here, if we think torch and then linear projection, right? So usually all of these models have just one linear projection at the end. So here, the in features will be out size. Okay, I will not actually tell you at the end what like I will ask as a question, that one. So that will be the in features, and then the out features will be that 10. So I don't, like there will be 10 classes, right? So we need to calculate the in features here. Then the model itself, Conv2d from our own implementation. So here will be the in channels 1, because this is grayscale. Out channels will be, let's say, 3. Kernel size, we can have, usually the first kernel size is bigger. So we can have 5, for example. Then the stride could be 2. Padding, if this is 5, I don't know, like maybe let's add 1 padding. So then we have this one. Then we can have the torch and then relu. Then we can have another layer of convs, right? So this will be the in channels will be now 3, and then out channels, let's say 6. And then we can maybe use, let's say, smaller kernel 3, and again use the stride stuff. So then we can have another relu, another convolution. And now let's see. So in very beginning, the outside in size was 28, right? So the out one will be the get out size. The in size is basically we already have that information. Input size with a large, like there is a constant given. So the input size is that. Then what was there? Then the next kernel size will be 5 for that one. I really don't like to repeat my code, but basically you could, maybe we should have that function built inside the Conv2d. Actually, that's fun. Why they don't have this? They should have this function built in Torch. So anyway, we have this one. Then the O2 after the first one is then the O1 here, and here we have different sizes, 3, 2, 1, right? And the next one is the same, basically. As you can imagine, the channels are not affected at all, because the channels are like they just repeated over all of the channels, and the number of those kernels determines the next channels, or actually if you use the dot product, then just the channel dimension determines the next channels. So here, my question now is following. So this, if you understand the theory so far, you should be able to answer it. So what is then the in features for FC? What size? What should be in features for FC? The fully connected linear projection. Meanwhile, while you think, maybe I will code this part. Maybe that will help to understand it better. So here there is out of self encoder, and hopefully that will help you to answer a question. Self encoder forward X, right? The same way as we always do. Then the Y here, the Y prim actually, is then passed through this self out forward out, but before that we need to do the flattening, because we cannot use just what's coming out from the encoder, because the linear layer works just on the last dimensions. So that's why we need the flattening. So we are flattening by VeA of, so we can also rewrite it a little bit so you can understand better. So the batch size here is in the first dimension, size. So somebody is saying that 10, but the 10 is out features. That is what we want to predict, right? But in features, this is not a guessing game. This should be calculated, by the way. So and I'm not asking the scalar number. I'm asking the what kind of variable should I write here, okay? Or what kind of formula should I write here? So it's all of the necessary elements are on the screen right now. There is nothing like this is not a guessing game, and it's also not a like calculation game. It's just having the correct components in the correct order. So here the x of size 0, batch size, -1. So what it means basically is following. Here the shape of the x here. By the way, question still holds. I don't know like who's gonna get the correct answer, but nobody yet given correct answer. So x size is so it's actually batch, comma channels, comma width, comma height. So this is our stuff here. Then this is a channels in actually. So then, and also of course weight and height in, right? And then afterwards, after this part, then out here will be the channels out, width out, height out, and then after this part out flat, we will have batch and some kind of features here. So if you understand that we just like combining everything that we had before there. So not combining but concatenating basically. And then after the y prim we will have the I actually given too much already, so you should be able to answer this question immediately. The answer is almost like in your face. So here there is a output is of course 10 class distribution of probabilities. So that's the easiest part. So what should be FC in features? Features. Let's ask again. So maybe looking at the code again with additional information, you'll have new ideas. So, and looking at what we already calculated in the constructor, you should have new ideas because it's quite a lot of stuff already given there. By the way, if you don't understand any of these lines, you see the line numbers, you can ask the question about some line, or you can ask anything with this code that you don't understand, but I need that answer. And if I don't get that answer, I assume that you kind of don't understand what's happening. So you're saying that in features should be a batch size. Okay, Kristaps is one who is interacting. What do others think? Really hoping that you're not doing the guessing game, because like again, the in features we define in the constructor in this part of the code, right? This part of the code is given just for you to better understand the situation, how the shapes are propagated through the network. So, but my question is about line 101. let me check. I think like if you do the homeworks, then you should be kind of on the page with the importance of the batch size in some other way. So as you like, I will start like answering some parts. Like batch size is something you never touch. You never touch batch size. Batch size is something that is independent at all. Like this, like so you want to repeat all of the operations across all of the samples of the batch. That's why you don't care about batch size. You want also to make your model like ready for the production. In the production, maybe you have just one image that you want to classify, and again, then you don't need the batch size, because if we just pass one image as like we don't want it to be dependent on the batch size. So you never touch a batch size. There are some, you will see today there is one function that kind of touches batch size, unfortunately, but at the same time it's not like right now that used already. There's better functions already, but yeah. So still no correct answer. So calculating, I like that you're giving at least some feedback for me. So the formula that you see on the Jamboard on the slide number 3 is the get out size formula. So that we already implemented and that we already applied 3 times here. We have O3 here that is not used yet. Maybe, like most likely, we need to use it for the in features, but how to use it for the in features? So my question is, if you think logically about these shapes, so again, maybe we should even rewrite it down even more. So here, let's say the batch size could be 16, because I think we have 16 batch size. Then the input is 1, because this is a grayscale. Then this is a 28 by 28 image, right? So after the encoder, we get 16 batch size, and the channel count here is, as you see, actually there is a bug here, nobody told me. The in channels should be 6, and out channels, maybe we can change it, maybe we can leave it as it is, but let's increase to 12. So the out channels are then 12 here, and the width and height is actually this O3 here. So now I'm giving you so much that like giving you everything basically. So O3 here. So then this is like, next thing is we want to reshape it, or view means just reshape it. So the reshaping operation, hopefully you understand it, that it doesn't change the data at all. So if you have, let's say, something like this, right? If you have, let's see. So if we would have 1, 2, then 3, 4, something like that. And this now is in the shape of 2 by 2, I think, yes. So the shape is 2 by 2. And now if I want to reshape it to, let's say, or what we could reshape it to 1 by 4, for example. 1 by 4. So this then reshaping it would mean that I would change the allocation of the array in memory, and this would create as 1, 2, 3, 4 like that. So it would just change around some like the location of those values. So that was just an example. What is this weave or reshape function? So, and the -1 means everything else. Basically, this -1 is the exactly same value as here in features value that you're not given me yet. So I'm still hoping that you can come up with that answer. Please think about it, please, and type in the chat if you will not able to come up with correct answer, let's say in 5 minutes, then I will give it to you. But this should be something that you can do yourself. So maybe if you don't know how to code it, like, but even though it's like super trivial now, then maybe you can write it in your own words. What do you think? What it should be there? That would be a good beginning. But kind of, even if you answer wrongly, then it gives me an understanding of the depth of the knowledge. Because, like, for example, if you answer like Christoph did, like about the 10 or like the output classes or the batch size, it kind of makes me think that you don't understand the flow of the variables. Like the batch size is always there. You never touch the batch size. Then the output is already given. The 10 class vector that we want to predict as a probability distribution. So that we also don't touch, but we need to understand what's coming in here. So even wrong answer would help. Maybe you can guess something. So 19, you are calculating something. I was asking to not calculate, to just give a formula, but okay, let's then calculate it. I was not ready for doing the calculation now. So let's yes, thank you. Another interesting question. FC stands for fully connected. Yes. So this is a fully connected or affine or linear projection. So the affine transformation is the one that we used with the robot arm. So this is just so W by X, the dot product plus B, or you can think of it as rotation by vector plus translation. So that's what it is basically. But still, I don't have the answer except the one that Arman's calculated. I need to recalculate it. I was not ready for doing the calculations. Maybe let's see if that's the case. So okay, maybe I should open some temporary code here. So I don't want to write this by hand. I just want to use this code here. It's like that. And then the input size, we know it's 28. And then let's look what is the O3 here. I would like to use just O3 variable there, but if somebody is calculating it, we can check it. So it's 4. Okay, there is another bug here, but this bug is not that serious. So I mean, like you could give me answer even with this bug. So there is a flooring operation needed. There is if the kernel cannot reach the end of the matrix, then it will be ignored. So if there is like some row at the end or column at the end that is not dividing equally by the stride, then it will be ignored. So that's one thing to keep in mind. That's why maybe these, but at the same time, like often it doesn't matter at all. So let's see. It probably matters a lot in the first layers, especially if it's like if the objects can be located in the close to the border. So let's see if I run it again. So it's 4. That's great. So this is 4, and now I will calculate if your answer is correct or not. So I already see that this is not correct answer. So unfortunately, this is not correct answer. I don't know how did you came up with 19. I don't know, like in any way I cannot come up with that number. So anyways, like if you would give me a formula, that would be great, much better. But okay, we already sitting on this time so long, and like I already given you the answer in your face, but nobody can see it. So here, as I said, in the forward pass is your hint here. So the forward pass tells that having the output of this is 16 by the batch size, so I don't care about 16, so that's batch size. So that is then 12 channels. We have 12 channels. O3 by O3, and then we do the reshape. Reshape means that we will multiply these three together and have the batch size untouched. So that's like a super simple, in your face answer all the time. So here what it is then, 12 O3 by O3, and the multiplication O3 by O3 is because this is a two-dimensional matrix, right? So there is a like small image with the depth of 12. This is called feature map there at the end of the convolutional network, and we need to like squeeze it, like, or reshape it or VeA it in different way, and this is the only way how to do this. So hopefully now let's see if is it clear. So is it clear? Plus, minus. If it's not clear, then please type in what is not clear about this operation, or in which line, or something else. Then I can help you out, because that's a bonus for those who are joining the live session. Then I can help you out. Otherwise, you're on your own then. So, and as you saw before, when you're asking even simple questions, I always answer them anyways. So, is it clear? No answers yet. So the answer is not 12. So if you see at my code here that I also shared on the Jamboard, this is 12 multiplied by O3 by O3. Okay, so it's not clear, but it'd be nicer if there would be some additional information. But okay, let's see. If it's not clear, then we need to try to start drawing pictures probably. Otherwise it will not be good. So it's out of the channels of the last layer. The last layer channels is important, of course, but also the out size is the important. I mean, like the 12 is something that is coded here. So maybe we can write it here, like, let's see. So out channels, there will be another variable we can add to make it sure that you understand what I mean here. So I added out channels here. That will be the out channels of our encoder, right? The convolutional encoder, and we multiply it also here. So that's why there is a 12. But I guess I need to start drawing pictures. I'm not sure how well it will work, but let's see. So let's try to somehow help out with understanding. So let's see. So we have first we have some image of let's say some trousers, right? I don't know, like this will be the trousers, right? So that's our input image, right? So this is 1 by 28 by 28. Plus, of course, there is a batch size that we ignore, because this is always like duplicated all of our operations times b. So that's the input, right? That's the x. Then I probably will not draw all of the layers, but at least some. So then what will happen is, after the first convolution that we do, so we are running this small kernel around all of this stuff, right? And summing all together and generating the output. The output then looks something like this, so smaller, but there are more of so the first one was just 1, then the next one could be 3, for example, 3 feature maps. So we the kernel is generating depth, so the deeper these images. So now this one is, let's say, smaller. Well, so this is and the output of this one. So here's the 3 channels now, and this is from the formula that I gave you, right? The formula that we just implemented. That formula gives this answer. So maybe the output would be 14 if this is like the case where, or maybe we can use exact numbers. Let me choose. So if I see here what is the 01 here, we can use even exact number. So the exact number for 01 is 13 actually. So just to see the process. So that means that if we insert the 28 in that formula and also the kernel and everything else, we get that output. So that's after the first convolution. Then we pass everything to the ReLU. The ReLU just do the simple ReLU function for every pixel in all of those maps. But as you see here already, this is 2-dimensional, this is 2-dimensional, and so on. So there's like the dimensions still stay. So then we have the next layer, for example. By the way, of course, here is ReLU, okay, right? Then we have the next convolution. The next convolution, let's say, produce 6 even smaller images, or the feature maps as they call it. So 1, 2, 3, 4, 5, 6. Okay, they are laid. I don't like how they are laid. Let's see. Okay. Like that. By the way, I hope that this will help out to understand. So if I'm showing this and this doesn't make sense at all, please let me know in the chat so I can try to talk about this in a different way, because otherwise like I'm just then spending time. So this will be then the next part, the next layer. So here again, batch, we ignore batch. Now we have 6 channels, and here we'll have something smaller. So let's say 8 by 8 or let's say 7 by 7 size of the 2-dimensional maps, these small ones, right? Then we would have another one, another one, another one, but I don't want to draw those because otherwise it will take too long time. But at the end, now we have the situation where we need to pass this stuff inside a fully connected layer, and the fully connected layer works with just with the one-dimensional data. So here actually we have, so let's write, so here will be fully connected, that works with in features as the, so the in features will be 6 by 7 by 7, because we need one-dimensional data. We need one-dimensional data, and out features, because otherwise I cannot do the dot product with the weight matrix so if there is many dimensions. So out features then are 10. The classes that we want to calculate. So I don't seem to understand why we're getting 3 channels also in smaller size. It's because we, so the question Arman's asking about why we're getting 3 channels in smaller size, that was what I showed you, but image how the algorithm works. But don't worry, we will just in the second implement the same algorithm, and then you will understand why it's reducing and why the channels are increasing. But this is not actually the problem here. The problem that none of you could answer was how to then convert the features from this to that, and that's why I'm just drawing this stuff here. So the idea is that if we have like all of this stuff here of these maps, we can easily, of course, if you think about it, like place all of these maps just one by one, like that, like if they are just stacked one side by side, right? So this is the first step, for example. So we stack them all like that, and this is just for the one batch sample. For every batch sample, we have a lot of these. So there are a lot of these. So then, and then the next step is we can unroll each of these small boxes. For example, we can concatenate them, put them in the list in like this. So let's say all of these guys are just the rows from this box, and then we get all of the next ones. Okay, so that's why, yeah, you're right about the roof and foundation of the house. That's great, because we could start by implementing the convolutional function. Maybe you're right about that. I think about it next time. Maybe we should start by implementing the function itself. But the question right now, it still was regards to understanding of the layout of the data. But let's please keep focusing on this one. So we can, let's say, so we can unroll all of these as from one box, and then we can unroll all of other the data from other box, from the 2D image, right? And create a vector that is just one-dimensional vector of that size, 6 by 7 by 7 by 7, right? And then if you have that vector, then we can do the linear transformation with that vector. So like that, and so on for all of these, and create just one-dimensional sausage. Create a 1D sausage for every B sample. So for every batch sample. So let me just double check this one, because no worries, we will go in the kernel algorithm as well. So the kernel function algorithm. So here is this part of passing 2D data. Actually, this is a 3D data in fully connected clear. So is this clear? Like how to pass? Then how it's like, just like if you think that function is like reducing the size and increasing the channel count, that's one thing. We will look at in just in a second. A part of that, is it clear? This last section, the one that I was asking all the time, of the like changing the data shape so that it would fit inside the fully connected layer, like not inside, but would be operatable. So, and then this out is then at the end, basically what you do is that you have the y prim is w dot c dot of this x that is now as a sausage sausage plus b plus bias, not of course the that stuff. So that's the last operation here. Okay, at least one person saying that's clear, so that's great. Now we move to the implementation of the algorithm itself, and hopefully then it will be totally clear. Also, maybe you're right that we should start by implementing that algorithm first. If maybe that was a confusing part, maybe you're right. But I was thinking about looking at this from a higher perspective and then going deeper. But we can do otherwise. Well, maybe we should do otherwise. So, anyways, let's then implement the algorithm itself. So, the algorithm itself. So we will implement it in really dumb way, but it will illustrate very well, I think, how it works. So let's say we all have the weight, so the kernel matrix basically. So maybe we should call it the kernel. So kernel, but okay, this is a matrix. That's why I will use the big letter kernel, or let's call it just K. Sorry. So this will be torch n parameter. So this the torch n parameter is like variable for the numpy code that we written before. So then torch float tensor, So we will have some kind of float matrix there, and this matrix will be of size of kernel size times in channels times out channels. And the one thing that I also want to do is torch nn init, and here we can initialize it in different ways. Uniform, so heavier uniform, gaming, so we can try to use the heavier uniform. So that's kind of popular way to initialize the weight matrices, so that they are not just random, completely random, or just like not also zeros. Zeros, as you know, ReLUs do not like zeros. We should not have too many zeros, right? So we can then pass this function there. So not function, but the instance of that parameter. And of course, this is a pointer, and that's why everything works. The pointers are then just initialized in that function, and that's fine. So we'll have this part. And now that let's start digging into the code itself. So the code itself will be really interesting. So the algorithm, basically, the kernel function. So the kernel function is simple, but the algorithm is interesting. So batch size, x size, of course we can get batch size from the constant, but we cannot ensure that always the batch size will be the batch size, because as I say, you can run the same model in production with only one sample per batch, and it should work. Like the batch is something that we always ignore. That's why we cannot just start using it. So that's one. So then the in size will be the, in size is the size of the dimensions of that two-dimensional feature map. So in very beginning, this is 28 by 28, but we don't know what it is, so we need to check it. So x size -1, this means that the last dimension from, so the last dimension from batch C width and height. By the way, you can imagine that kernels can also not be squared. So I mean, like they can be rectangles. Like I mean that, for example, you have portrait images. So maybe then the kernel could be different than the symmetric one. So then the out size. Out size is something that we can calculate, get out size, because we already have the function. In size, and then we need to pass the self kernel size, I think. What was the parameters? Oh, sorry, first was the padding. So that's important not to miss it. So self padding. I also need to double check, okay, there was a fine. Okay, in the previous function that I wrote, I gave the type parameters, that's why it worked. So padding, then the stride, stride, you cannot mess up the order. So okay, now we have the out size. So now the out matrix, or the feature maps that we will produce. So this will be torch zeros. So this is our feature map that we will generate. So actually I think we can just write float tensor, it will be the same stuff. So float tensor will be then the batch size, comma, the self out channels, and then out size, out size. So this is our template for the output. That will, in this template, we will put inside this matrix, we will put what we will calculate as an output. So that's great. Then the input, again, is not so simple, because we actually need a padding there. The padding, so we need to change the x actually. So the x padded. So we need to add padding to our image in the very beginning, and then for the feature maps. So we can have the torch float tensor. I really hope that this is initialized by zeros. Let me double check it. I want to double check it. Torch float tensors init initialized zeros, because as you know, if you have some vectors in C++ or C, then they, like, if you have arrays of floating points, that it's not that they will be zeros by default, that's for sure. So you need to double check that one. Should I use p-over float tensor? So, okay, this is initialized memory. We cannot use this. So this is important stuff. So this is exactly like it works in the C++. If you initialize some array, there is no guarantee that that array will be what you think it will be. Like it will not be zeros. It will be something like random numbers. So here this should be zeros. Then also here, let's say this will be zeros. There will be batch size. So then the x padded is a little bit different now. The x padded will contain the in channels now. In channels, self in channels. It will also have the in size, but it will also have the padding. So self padding times 2, because we want a padding on both sides of our image, not only on one side of the image. So, and also we want a padding for the height. By the way, this particular function that I'm writing is working only on squared images. If you will have like this rectangular image of the portrait image, it will not work. But we don't have time to make it too generic. So here the y padded, then we will insert our x there. So we will copy batch, we will copy channels, and then we will select our area. So this will be self padding tilde minus self padding. By the way, I should actually check it if it works like that. Last time, I think, or some time ago, we looked at Python arrays and the ways how you can mess your brain with Python arrays and have totally unexpected results. You just probably should double check this stuff before committing to it. Yeah, so everything except that area, right? So this will be fine. So then also the padding for the other one, and then the x, so we will store the x inside that area. Again, we already talked a lot about the storing values in the matrices and arrays. We already had a lot of examples before. I showed you how to debug it, how to look inside those vectors and matrices. So that's one. Then the other is, okay, so let's then start making the loop. So there will be like for I in range of 0 till, so let's see, x size. So this will be actually, so let's add another variable. I don't want to have too many of them. So this will be x padded size, and this will be the last dimension of these guys, or we can just copy this one here, or we can actually use the same stuff up here twice, so that you don't need to copy it twice. It doesn't matter, like the way how you write it, the same stuff here. So x padded size is this in size plus padding times 2, and this is at the end of those two lines. So we go from 0 till that part minus self kernel size, except let me think. Okay, this one might not be exactly like normally you would have the kernel as the input of that one. But still, in general, the algorithm works this like very similar way as normally these convolutions. So we go by stride then. Anyways, this will produce the desired result anyway. So this is not totally accurate, but close enough. So then we go by the height. So we went by the width, and now we go by height. So that's great. Then the next part is we need to select out the region that we want to apply our kernel. So let's select that one. So X part is that region from X padded. And we want again copy batch, copy channels, and then use only the I plus I self kernel size and J till J plus self kernel size. Again, very beautiful that we can use these matrix selectors to select regions like the boxes out of the matrix. So if you don't have these kind of nice features that NumPy, PyTorch and Python provides, it would be really long code to do this stuff. So we select out these regions from the matrix. And now we need to somehow store this value inside out, that is our output, that we also can put it here as an output. And so to do this, we can then we need to do some additional stuff here. So one is we will have some counter for I out. So this will be 0, and also for J out, because the output matrix is smaller than the input matrix. We cannot just copy it just from I and J. So that's one. Then the J counter will go +1 here, and the I counter will go +1 here. So that's one part. Then the other thing is the kernel matrix that we have. We need to also reshape it again. So we need to reshape it like in very similar manner as before that I showed you about the idea that we don't change the data but just the layout, because all of those kernels, so in this case it's a little bit different reshaping, and maybe I should write it the full way. So I will write it in a full way. So here will be the self kernel size multiplied by self kernel size multiplied by input size. So in channel, so this is the this part, or maybe I should just write it as -1 and add as a comment so you don't need to write it so long. So this is the -1. This is -1 means everything else. So multiply together kernel size times out, so times in channel, sorry. So we want to have that part of these X parts that we cut out of our images are reshaped in this manner that we can have multiplied by all of this kernel in channels and produce the produce this out channels. So the way how this then works in this part is in this part, this is here X part reshape. So here we need the reshape, not view, because we are selecting something out of the matrix and it will not work with the view. So here we have the batch size, and again -1. In this case it means again, so the same stuff as here. So we have basically what we did with the linear regression, with classification, with very simple models without the images, is that we want to have two-dimensional vectors here. So I mean the two-dimensional matrices here. We don't want to have, so here is the two-dimensional matrices of K and one-dimensional vector of X part. So the batch size we ignore, and this is just a one-dimensional vector. So we have the one-dimensional vector multiplied having the dot product by the other one, then we can then we would get output of that out channel size, and then we can put that one inside our desired location. And again, the procedure here is kind of funny, because we could of course drop let's say we could drop the in channels or do some for loop or whatever, so, and then sum it together, but dot product does it already automatically. That's why we can just include all of those parts inside here. So what I mean by that is that we could combine batch with, let's say, kernels by kernels, and then work with in channels and out channels, and then have additional for loop to sum everything together. But I don't want to do that. Like, if the dot product does it automatically, why do I need another for loop there? So I don't want to have another for loop here, and it will not illustrate the situation. It will just make it too complicated. So here, let's say we now have this out part, and out part we get by this. So let's see. So x part by the matrix multiplication by the k, or the dot product, and now this one will be the size of the batch size, comma out channels, as I want it to be, because the out channels is actually copied just in one pixel of that new feature map. If you go back in the slides in the Jamboard, what I'm talking right now is in the slides number 3. In slide number 3, you see that image where you have just one pixel value, and this is what it means. So, and now I put this value inside that out matrix. We use the batch. Just a second. I have one. Okay, so I'm back. So here, this one we copy, this one we copy. So the batch we copy, the channels we copy, because the channels actually here is the out channels in this case. So, and that's why we copy it. And here we have the I out, comma J out, and we put inside out part. And I think that's about it for the convolutional layer function and the kernel function. So the kernel function itself is actually this line. So this is a kernel weight matrix with a dot product, and that is the kernel function, and everything around it, this is the algorithm for applying that function. Basically, this is like kind of a framework for that function. That itself is a function, of course. So anyways, if this will work and there will not be a bug, then I will copy this code in a second inside the Jamboard. I guess I need to copy it anyways. So we don't have that much time, but we will need to. So I will copy this part, and if there will be some problems, then I will fix it later, because we are also missing the loss function. The loss function, you definitely know how to implement yourself, because this was required already many times in this course. So here in this part, and by the way, if you don't know how to implement those loss functions, you can of course ask. This is one thing, but the other thing is that if you don't know how to implement that is indication that you have not done the homeworks probably, because I think like the best performing people right now in this course who are doing the homeworks, Like there are absolutely no problems of implementing the loss functions at this moment. So because in the homeworks you have step-by-step instructions what you need to do if you start from the first homeworks. So here, and they also show those things in the live sessions. Okay, so I just copied this code inside the slide 6, but I need to now to go down to the loss function to fix that one so we can run something together. So the loss function is a categorical cross entropy. Maybe I should ask that before implementing, but anyways, we don't have time to talk about it again. But this is like really simple loss function from information theory related to the entropy functions and the divergence of the KL. So anyway, y prim and here e minus 8, so some kind of epsilon. So the loss function, I will drop that also in the Jamboard. So only this small line that we need to add. And hopefully we're already good to go, at least for this part of the code. Oh man, what is this? Okay, something did not copy, right? Okay, now it will be fine. Okay, so that's added to the Jamboard, and I need to check if I don't have bugs here. Maybe I have. Okay, no, not here, because we were talking a lot and writing a lot of parts, and maybe I messed up something. So we have some problems here, unfortunately. So this is a problem with the backprop and probably with the most likely with something with regards to calculations that we had. Grad can be, oh, sorry, right. The loss function will not work like that. Of course, nobody corrected me. So the loss function works from scalar output. So torch mean, we need to calculate the average of the categorical cross entropy or negative log loss or whatever. So they call it in different names. This is basically the same thing. So the mean value will work, hopefully. I will run it again. Okay, now it works, but the loss blew up immediately. So it blew up, and this is not good. So let's see what we can play around. So technically it works. So maybe we can change initialization. Gaming uniform, but I don't think that will give an effect. So we'll see. Maybe we'll need to do some additional stuff here. Okay, the loss is immediately not good. Let's see if I add let's look at the loss after the first iteration. Hopefully it will illustrate a little bit the situation. By the way, the code is in the Jamboard as well, so you can follow up on that. So loss is n after even the first one, the y prim, but n loss, so that means there is a right, I forgot about it. So nobody again like reminded me. The classification is not possible without some kind of limiting factor for the categorical cross entropy. In this case, that limiting factor is the softmax function. So here we're missing the softmax function, softmax of y prim. And let's say, well, this is actually logit. This is called logit. And if you would use something already pre-made and don't understand what you're doing, then that part is actually not required in some of the pre-made code. That's why maybe I was forgetting it. So, but the softmax is very important, as you know. We talked about it the last time, I think. So I will update code in slide number 4 as well. In slide number 4, I added the softmax at the end of the model. I will also mark it a little bit so the people who are coding can see that this part is important. Okay, that's why we had the negative, like undefined loss. If I run it again, now it works. Great. The accuracy increases, the loss decreases. We have successfully implemented convolutional function, and it learns the convolutions by itself. So that's great. There are a few other things I know that we're running quite fast and we don't have time, so you'll need to finish this code yourself from the Jamboard as well. But we need to add a few extra things before we end today, because I will also have a small homework for you, and because this course is quite packed, actually now I'm realizing that if like some students are kind of like not getting along, then might be difficult. But still, we will talk about a little bit about convolutions tomorrow as well, but then we will move to the next topic. So here we need to fill those to-dos to run this on GPU. So to run this on GPU, what you need to do is to use then, so one thing is that we can detect if you have GPU. So by the way, if you see, I limited the dataset length here. So the dataset length is limited intentionally, because when we run this on CPU, we cannot wait forever, right? So then torch CUDA is available. So is the CUDA or device or the GPU available? Then in that case, we will call device CUDA, so that we want to store this on GPU. That's one. Then we have max length. We say that we will not limit the max length of the dataset for if you have GPU. So then the next part is we go to the to-do a little bit down the road. So maybe I will add those snippets to the code as well on the slide. And then we will end this session today by running the same code on the Google Colab on actual GPU. And you will do this yourself also later. And as for the homework, I will give you the task to construct a very simple convolutional network using the torch and then convolutional function. So not the one that you build, but if you want, you can use your own function as well. I mean, like it's not like the torch and then convolutional function is more powerful than our function, but at least now you should understand how it works. So if we go now down to the to-do here with the model, so we need to pass model to device. So this is one part. Again, let me copy this part as well to the Jamboard. Then the next part is then x is x to the device and y is y to the device. So what I mean by these functions is that I'm moving the memory from CPU, from RAM to the GPU. So we are moving the vectors, we are moving the weight matrices, we are moving all of these things to the proper memory location. That's why we need those. So that's fine. The Y prim is already on GPU now. The loss is also on GPU. And here, if you look, I moved it back to the CPU. So that's again very important part, but that's already included here, is that if you want to access the results of your outputs that are calculated on GPU, you also need to use these CPU functions, and I added them as always. So I mean, like they work regardless if it's like on the CPU or not. So that's just a safety measure. So that's great. So far so good. Everything is on the Jamboard as well. And now I will open the Google Colab and show how to run this on the GPU using the same code we just did. And then for the homework, you will have very slight modifications of what we had with using the built-in convolutions. By the way, the one thing that maybe people do not realize is that for at least last 2 sessions or maybe 3 sessions even, I give homeworks easier than the classwork. So that is intentionally. I don't want to make that your homeworks are crazy hard. So what we do in classes is much harder than what you need to do in homeworks. And if you don't do the homeworks, then basically that's too sad. So anyways, let's go to the Jamboard. So this is not a Jamboard, this is a Google Colab. I just copied the code that I made with you together. Now, if I change the runtime to GPU here and save, and these cats are walking and I'm saying the connecting, so it's connecting to the node with GPU. And now if I run this stuff here, in a second, hopefully it will start downloading. So it's downloaded the dataset. And then it will start training. Okay, I forgot. We have some other issues that I definitely know will be an issue and it will probably not work. Yes, it did not work because I forgot something. So it says that the tensor is on the CPU, but everything else is on the GPU. So of course I have a problem. So I forgot that we created small templates. We created these small templates to explain code a little bit better. So if I go in the convolution, I will add also that to the Jamboard. In the convolutional layer, in the forward pass, I created out zeros and I created X padded zeros. These also are now located on the CPU. So I need to move that to device, and also I need to move this guy to device. Basically everywhere where you have something in a forward pass, because the construction part is covered. So construction part, you don't care that you have device or not device, because in the construction part, the model already takes care of finding the parameters and placing them on correct device. But in the forward pass, this is something that model cannot predict what will happen in the forward pass. This is different from TensorFlow, where you compile everything before. Here you don't compile everything before. So this is on the slide 8. I added these 2 lines that I changed. And now I will try it again. I will try it again in my Google Colab. We'll try to run it again. So this model, I don't expect excellent results from this model because this is very shallow neural network and with a very weak convolutional function. But anyways, I hope it will work. It's also fun that it shows in the bottom what it is executing. Like I think some time ago it was not like that. So now it's running on GPU and it's showing that it's calling this cell and then the forward functions. So that's great. So it's running over the whole data set of the whole epochs and stuff. That's why it's taking a little bit longer, but it would take like crazy longer on the CPU. On GPU it works like much faster. Maybe it will take, let's say, 2 minutes or 5 minutes. On CPU it might take half an hour or even more. So, and also, by the way, again, my function here is not that great. Okay, I really should not wait on this. I will kill it because I forgot that I was planning to show you this Google Colab stuff with the Torch NN convolutions, but this is our own convolutions. In Torch NN convolutions, they don't use for loops at all. So these for loops are making it very slow right now. If this is something that you can parallelize on GPU, and like NVIDIA CUDA library actually implemented like very fast implementations of these things. So that's why we should not use this one. Anyways, for the homework, I will ask you to implement the same stuff what we did before, but without using our own implementation, but Torch NN CUDA, I mean Conv2d. So that will be one thing, and the model will be given as a like a graph of what you need to implement, and all of the parameters will be a little bit different. So you will still need to code, like, and think about it a little bit. But the task will be a lot easier than what we did right now. But still, you can get points for completing also this task. So I know that what we do right now is a little bit challenging, like especially for people who are not submitted the homeworks properly so far. But as I said in the very beginning, we were going step by step. We started with like very basic math, and now we are doing all like more difficult stuff every time, and we will keep doing more difficult things in future. So like the only way for that I can encourage you is that you can build really like smart, awesome, like crazy deep learning AI models that can do almost anything. And the way how to get there is by diligently and carefully filling the previous sessions, and like not skipping stuff. If you start skipping stuff, it will be harder and harder. So we meet tomorrow. Hopefully, like at least the things that we are building are fun. Hopefully also the process will be more fun when the more you understand and the more you do this in practice and do the homeworks.